Hey, as your boy Chili here, welcome back to Chill. This video is going to be a little different than the other videos in this playlist. It might even be removed from the playlist at some point. Essentially what this is it's kind of like an interim update on my tentative prototype draft designs on what I'm trying, the direction I'm moving in the graphics part of the framework, which is, probably going to be the meatiest part of all. And it's been a few months. I still haven't added videos to this playlist because I haven't finalized this design. And it probably won't be finalized for a little while yet, but I'm hoping to get some more time. And also, one of the reasons why I'm making this video is a community member, Red Skittle Fox, talented guy. He has expressed interest in collaborating on this stuff. And so, hopefully with his input and help, we might be able to get some momentum on this. But, part of that will be I'll have to kind of like give him a bit of a debriefing, explain to him, what my goals are, what the constraints I'm working with are. And I figured, instead of doing that just one-on-one with him in a Discord call, maybe I could just make a video that explains my ideas and does a little walkthrough. And then I could share that with everyone. And then after Fox watches it, then, we can do a call and kind of, discuss any questions, any ideas that he has after that. So that's why this video exists mainly. It's just to kind of, keep you guys in the loop and also to serve as a debriefing for Fox or anyone else who wants to help contribute. So that being said, this video is going to have two parts. One is going to be where I explain the current prototype architecture and the ideas behind it, and part two is where I talk about what are the problems I'm facing, what are my aspirations for this thing, and what are my ideas of the next steps going forward. Okay, so let's talk about the architecture. So at its base, we've got two classes, device and render pane. Device represents the adapter, and it basically just wraps around a ID3D device and that concept. So in D3D you have your device, and you use that to create all your things, to create your contexts, or your in D3D12 would be your command queues, and to create your command lists, and to create your swap chains, I guess, probably. No, I think that's DXGI, which is why I have the factory in here as well. But essentially, device is being used to create all the things, to create all the resources, not for executing things, for rendering on a GPU, but for creating all the pieces of the machinery. And you're going to have one of these, typically only one in your process that represents the adapter. And then we have the render pane. And the render pane, you're going to have one of these per window. Because remember, I'm trying to push the idea of processes, games that have multiple windows. So this is very much designed with the ability to run multiple of these at once. And it's an encapsulation around two things. Because it binds to a window. It's going to be the swap chain, right? The swap chain is the thing that binds your Direct3D stuff to your window. When you create a swap chain, you have to specify an HWind. And it's also going to encapsulate naturally a command queue, direct command queue, because you always have your swap chain is always associated with a command queue. So those two things are the main things that go into render pane. And I've also added depth in there, although that might be pulled out at some time in the future. Now, just gonna wind back for a second. The main idea of the whole graphics system is that you are gonna have a set of interfaces, a surface level interfaces, which they're not specific to any one API, Direct3D 12 or 11 or Vulkan or whatever. They won't reference anything specific to those. So those will be your generic top level interfaces, basically. And this is what all the layers above the platform specific stuff That's what they will all bind to. So you can swap out between, Direct 3D 11 and Vulkan or 12, and all the stuff above this layer won't care what it's working with. That's the ideal. And then you have the implementations of these interfaces, which will be specific to, an API like D12, D11, Vulkan. So that is what we are working with. So right now, I haven't implemented it yet, but that's what I'm actually going to be working on next, is pulling out all the interfaces, figuring out what interfaces go into the surface level and what are going to be just in the platform specific layer. So before we go any further, let's take a look at a little diagram that I made. So here are all the major players, all the guys that you see around here. They're in this diagram. So you can see, like, I color coded it. Like green means like creating, and blue means this is like an aggregate or completely owned by the thing that it's associated with. And white just means some kind of association. So you can see that every window has a pane associated with it. And device is for creating a whole bunch of different stuff. So what else do we got here? Well, we have texture, which is created by device. And this is basic texture loading code, which you should be familiar with if you have looked at my shallow dive into D3D12. Should be familiar. If this is very foreign to you, then you should probably check out that series. But yeah, we're just loading image using DirectX Wick code from DirectX Toolkit or DirectX Text. I can't remember which one. We're generating the bitmaps. We're doing this on the CPU because that's just easier. They got a function for it right here, and I just use it. And then we load over to the GPU, and then we copy from staging to standard texture resource thing. That sort of deal. So that's in the constructor. And the texture also has the ability to write its information into a descriptor. You pass it a descriptor handle, and it will write its information into there, and that's how it gets bound to a pipeline. Very nice idea in there. But it would be annoying to create these one after another serially. So what I've done is I've made a resource loader, and what this thing does, it has a command queue. Because part of creating a texture is you've got to give it a command list, because it has to execute copy commands, has to transition barrier. So you got to have a command queue to execute that on. And what I'm doing with this resource loader is it has its own command queue, and we have a little function called load texture. And this is a little beauty here. It uses the state async, which on Visual Studio has its own pool of thread, has its own thread pool, and so we can call load texture, and that will spin up a thread task, put that in the queue, and so we can run these things concurrently. Because a lot of the constructor in texture here, it's running CPU code for loading from the disk and processing and generating the MIP levels. So it'd be nice to run that in parallel on multiple cores, and that's what this enables. And it also enables us then, after that, you execute the code, you execute the commands on the GPU, and we don't have to wait for all that to finish. We get back a future. So we can queue up a bunch of textures and just let them run in the background while we do other stuff. And then when we need the textures, we call get on the future, and we get them out of there. So that's a nice little thing that I've made there. So here we can see devices, resource loader. Resource loader is creating the textures, and those go into a sprite codex, which is a very simple thing. This, it has a descriptor heap, so we can't pull it out into the layer of stuff that doesn't care about your platform as it is here. But it's essentially just, a vector of, the sprite atlas is just textures plus the handle, the descriptor handle for the shader resource view. So it's just an array of textures, but it also carries a heap. So when you're going to do rendering, you can bind basically this collection of textures to the pipeline, and then your shaders can access textures by index. When it's time to render, you get a pointer to the heap, you bind that to the pipeline, and then your shaders access the textures in the heap. This is the implementation here. We create a heap, and then whenever you add a sprite atlas, which is, just a texture, you're going to use that texture's write descriptor method to write its descriptor into the heap of this sprite codex. So that's this bad boy here. Now let's go back to Paint. Let's look at command Q. This is mostly just ripped from my Shallow Dive series, but the command Q encapsulates, of course, an ID3D12 command Q. Also the fence that is used to synchronize on that command Q. And it has a pool of allocators and a pool of command lists for that command Q. So you can reuse your allocators, you can reuse your command list. So this command queue is used to submit command lists, but you can also get empty command lists from it. So, and you can get, values that you can use for synchronization. So what you do is you call get command list pair, which is this thing, which is just a struct that combines a command list with the command allocator used with it. You pull them out, and then you can use them in different places. And the main place where you use that is in the sprite batcher. So the sprite batcher is the heart of all the rendering that we're going to be doing. So again, if you look here, you've got an association with your command list and your sprite batcher, because what you do is you use the pane, you start a frame, or you do a begin on it. Well, I forget what it's called. Then you get a command list from there, and you give that to your sprite batcher to start its batch. And then you're going to draw sprites, which is going to tell it, okay, use this rect from this index in the sprite codex to draw. And it's going to build up basically a list of sprites to draw. It won't draw them. It'll just build up a list, basically puts it in a Vertex buffer. And then when you're done adding all your sprites, you're going to finalize that list, which will, write to the command list, the draw command, everything. Then you'll finalize it. It'll spit out the finished command list, and you feed that back into your command queue to say, okay, here's the finished command list, queue this up, and, execute it on the GPU. So let's take a look at the sprite batcher. You can ignore this. This is just some stuff that I did for testing. I wanted to test the performance differences between using virtualized interfaces versus non-virtualized. Just a virtual call overhead, which I found to be, for the most cases, not really an issue for us. So we're not going to worry. We're going to virtualize a lot of functions if we find a benefit to doing so. But anyways, so the sprite batcher, you got your start batch where you give it the command list. You also give it some fence values to synchronize on. Then you got a draw where you tell it which sprite atlas to use, the source, the dimensions you want to output to the destination, the position you want to output in the destination, what's your rotation, what's your scaling. So you can do a lot of per sprite transforms with this sprite batcher. This is the interface, by the way. The actual sprite batcher with the constructor, you can see here that you got to give it the dimensions of the target, basically the render pane, because it's going to have to do some conversions between texture coordinates and the pixel coordinates of the destination. You also give it the sprite codecs that it is going to be using. I might add functions to change the sprite codecs on the fly, but for right now we just set it and forget it when we construct. Also give it a max sprite count because it needs to know how big to make like the vertex buffer and the index buffer. And maybe in the future I'll make this so I can grow dynamically, but we'll see. But look at the member data, we can see there's a lot of stuff in here. And one of my goals is going to be, taking this monolith of the sprite batcher, breaking it up into smaller components so that they can be composed, swapped in a lot more easily. Like if you want to change the drawing effect, for example, different shaders doing different special effects when you're drawing, like tinting the sprite or whatever, You want to be able to make that composable. But for right now, here it is. You've got all the stuff needed basically for rendering. We got like per frame resources, which are the vertex buffer. Vertex buffer changes every frame, and you have to maintain it until the command list finishes executing. And that's where these fences come into play to determine, when a vertex buffer has been finished and we can reuse it again. Now the indices don't ever change right now for this situation because it's always quads. So it's always, 1, 2, 3, 4, 1, 2, 3, 4. So because of that, we actually just fill the index buffers once at the beginning with the pattern, and then we can just reuse the same one and we don't have to maintain it per frame. So it's a very nice little optimization that we're doing here. We got the sprite codex, of course, command list that you pass in. We got the root signature and the pipeline state, very important for rendering. All that good stuff. So if we look at like the implementation of the sprite batcher, let's just take a look. Biggest function is the constructor, because that is going to create all the stuff needed to, configure the pipeline. So, we're defining the root signature and compiling that thing, and then the pipeline state object PSO, all this stuff for figuring out what shader we're going to use. So I want to make this a lot more composable, injectable, configurable. But for right now, it's just hard-coded into the constructor. And then when you start batch, you're going to move in your command list pair that you're going to be using for this batch. You're going to set your fence values that were, acquired at the same time you acquired this command list pair. You're going to get your per frame resources out of your pool based on, your signaled fence value, so you know which ones are available or whether you need to create a new one. This thing, it goes down two paths. It's either going to create a new one if there are none available in the pool, or it'll pull one off the pool if there is one available. The other important thing is that you're going to map into that vertex buffer from the frame resource so that you can, stream the data across the PCIe bus. Sprite Batcher has a global transform you can apply for your camera, in addition to, the per sprite transform that you can get in there, so that it's done with a constant buffer that's set with this function. Well, I mean, the matrix is set for the constant buffer is actually only set, I think, when you end a batch. Now, every time you draw, this is an important part of it, you are going to basically build up. The only thing that goes to the CPU or the GPU per sprite instance is vertex buffer information. So we are going to build up our vertex buffer. So if we look at the definition of vertex, we can see it's got position in world space, it's got texture coordinates, and then per instance transform information, translation, and scale. We're not going to stream across a whole matrix or anything. I found it's more efficient to do the trig calculation on the GPU side in the vertex shader. So we just give it the angles and stuff, and it's going to build a matrix in the shader right here. It takes in all that information. It builds up a transform. It concatenates that with the camera transform, and then it's going to use that per vertex to transform the position. So what we do is we set this vertex up. We create like a local cache of 4 vertices for the quad, and we fill it all up here, and only after it's all set do we mem copy to the GPU. And this is generally more efficient. I did some performance testing and I found it's a lot better instead of just writing directly to this vertex upload mapped memory. Build it all up, make sure you got all your ducks lined up, and then write it byte by byte sequentially. And that's much better for streaming out to this uncacheable write combining memory. And then when we end batch, this is where we actually do all the drawing. Also, if the index buffer hasn't been initialized, we write commands to initialize it first here. But this only happens the very first time you draw a batch, and afterwards you can just reuse those values. But yeah, it's a good idea. Even though I think it's not technically necessary, but unmap the memory that you mapped with the vertex buffer. Give it a little hint on the range that you actually wrote to in there. It can do some good work, especially in debug. And then you're setting your pipeline state, you're setting all your stuff up, you're just setting up the whole shebang, and then you do your one draw call. Very simple. You draw your batch of, 500,000 sprites all at once, and Bob is your uncle. And once you're done here, you're gonna you basically, this isn't actually drawing anything. This is just recording commands onto a command list. Now you're gonna poop out that command list, and that is going to be fed into your render pane, which is going to put it into the command queue owned by that render pane. So that is how babies are made in our view of the world. And that is by far like the most complicated part of this, because that's where all your drawing is being done. But it is incredibly efficient. Again, like I said, you can push 500,000, decent sized sprites out there and still maintain 60 frames per second. And the bottleneck on my machine is very much on the GPU. The CPU, because this sprite batcher, it's very nicely multi-threaded. I can run it on 4 threads. I can run it on 8 threads, and it's doing great. But the bottleneck on my system is the PCIe bus. So you're not going to get double the performance with double the number of threads, because you're going to run out of bandwidth streaming out. Where is it? Right here. This is the bottleneck. And the only way to fix that is to make the Vertex data less, which could be done in a bunch of different ways, but in general is not so easy. So yeah, for my 2080 Ti, I can do 500,000 sprites at 60 frames per second, and nothing I do on the CPU side is going to make that faster. By the way, I should mention that on the CPU side, the bottleneck is this, but the bigger bottleneck that is limiting me to 60 frames per second is just the execution of the draw, which could either be executing this Vertex shader, which has to do some stuff like sine, cos, and a bunch of matrix multiplies, or it could just be the fill rate, which I can't do anything about that. Well, maybe not. We'll see. Now, the last thing you see in this diagram is a sprite frame, and this is just an encapsulation of the idea, like a sprite codex has a bunch of different animation frames, maybe from multiple sprites, all in a single texture. And this is just, saying one frame of animation from one sprite on a specific texture in a specific codex. So there's actually nothing, let me see here, where it is, sprite frame. There's nothing in here that is specific to Direct3D or 12 or any API. So this is actually going to be pulled out of this D12 folder and just live in the platform agnostic layer. But it just knows to draw itself to a sprite batcher. And then you can have a list of sprite frames, and that can be an animation sequence. And then you can have a collection of animation sequences, and that can be a sprite blueprint. And then you can have a sprite instance, which is just holding the state information for a specific instance of a sprite blueprint. Like, what is the current animation, and what frame is it at on that animation, what's its position, what's its rotation, all that information can be held in a specific sprite instance. And that's just this tentative stuff that I'm doing here. I didn't put it in these folders over here because this is just test stuff, and it's all going to go away anyways. But I was testing to see what if I just did I threw a ton of virtual calls into here? Does it just slow right the heck down? And it's it didn't make a difference for me because my bottleneck was never CPU, and even virtualizing everything didn't make the bottleneck the CPU. It was always the GPU. So that is telling me that I can have a pretty free hand on virtualizing, even the per sprite stuff, which is the most iffy one of them all from a performance standpoint. But anyways, so that's that. And if we look at, how I'm actually using it when I'm testing, I actually just jammed a big ass class inside of my main here. I just defined this whole class, and this wraps a window. So it basically encapsulates the window plus the render pane that goes with that window, plus the all the sprite batchers that go with it, and all the sprite instances and everything. They're all wrapped up in one of these. But here's where the actual main starts, and we initialize COM, we boot up our IOC, then we create the one device that we need, and we create the one sprite codex that can be shared by all the panes all the sprite batchers. We create a resource loader, and what we're doing here, we have a vector of futures. These are just future textures. I was cute with decal type here and defining them. I'm just being cute. But anyways, we have this vector of futures. And so first we loop over, we have an n sprite sheets, I think 32 sprite sheets. So we loop over each one, and we're just calling load texture and accumulating all the futures. So we basically launch all of these tasks, and they're going to be executed on a thread pool concurrently, so good performance. And then once we've launched them all, then we wait for them all to finish by, calling get on the futures and then adding them to the sprite atlas. So we're not doing any other work while the textures are loading, but we are loading them in parallel, utilizing multiple cores in order to do all like the mip-map processing concurrently, which is much faster. So once we've loaded all of the sprite sheets and we've got them all registered into the sprite codex, then we are going to create a number of windows. So like, for example, we could do 2 windows rendering our scene at the same time here. And we just create active window, which is defined up there, and we give it its own index so it knows which one it is, and we give it the device because it needs that to create all the things, and we give it the sprite codex because that's where all the textures are shared between our different windows. And then all we're doing here is, this should be familiar, we're just looping, and if any of the windows are closed, we are going to delete them from the container, call their destructors. And we do this check every 50 milliseconds. But mostly, once we get here, this thread is done and it's just going to sleep. So all the stuff happens in the active windows. We go up here. Again, this code, none of this code is part of the framework. This is all just test stuff. But it's interesting because it shows how the current prototype of the framework is going to work. So we see here that the active window is really just a shell. It's going to hold a bunch of data, and all the logic is going to happen in a thread that the active window owns. That's the render thread. So what do we have in the active window? We have a construction semaphore that just lets blocks the constructor until the thing is actually started up. We have the atomic that signals whether the active window is alive or not. This is how the main thread knows to erase it. And we have the thread itself. So the thread its behavior is dictated by, I called it the kernel, just whatever the thread function. And again, this is just the stuff that was passed into the constructor. It's just forwarded onto this kernel, the index, the device, and the codex. So I created a little input utility here just so for my own testing, but this is probably nothing like what is going to make it into the framework. So I'm not even going to go over it, but it's just a very simple way of getting input from the keyboard. I want to do something better for the actual input system of the framework. But yeah, we get the keyboard, and then we create the window. We resolve it out of the IOC container. Okay, so window is also in the IOC container along with the logging. And we customize it by giving it a custom name, which is based on the index, and by passing in the keyboard that is going to be used, the keyboard object that is going to be used to get the input data. So keyboard is just kind of a hook into the input data that the window is collecting. So yeah, we create the window. We create the render pane by passing it the window handle. We have to create a command queue when we create the render pane. It doesn't create its own command queue. This all has to be hooked up somehow with the IOC system. Well, right now, none of the graphic stuff is in the IOC. Then we create sprite batchers, and we're going to multi-thread our rendering. So we're going to create 4 sprite batchers. So we just loop, integers from 0 to 3, and we create a sprite batcher. With the size, it needs to be able to accommodate n sprites, where n is, the number of total sprites divided by the number of batchers. Each batcher is going to take, 1/4 of all the sprites. And then here we release the semaphore saying up until this point, okay, construction is finished, the thing is now running, and so the thing that was constructing it can now unblock. But here in the future, we probably want to catch exceptions if they happen up here and marshal them up to the guy who who called the constructor. And so, we put it in a exception pointer, and then that would be thrown from the constructor in the other thread. But we're not doing that right now. We get ourselves a little random engine because we're going to create a buttload of sprites. So first we create a sprite blueprint for every sprite sheet that we have, 32. And then we're going to create an instance of sprite with a random blueprint for, number of sprites that we want to create, which right now is 1,000, but in my tests in release mode, I generally run with 250,000. And you can run up, if you want to maintain 60 frames per second, you can run up to 500,000 on my machine. 500,000. But yeah, we've got a bunch of distributions. Going to pump them into here, and we're going to use that to generate some random information for our sprite. Where is it at? What's its speed? We're not rotating any of them in here, although the calculations are being done for rotation, so we incur the overhead, but the test itself is keeping the same orientation. And then we got some stuff for the camera. Here's just some ranges stuff. A batch is a batcher combined with a range of characters. So we're dividing the range of characters into 4 equal size ranges, and we're zipping that up together with the batcher that's going to be used with that. And then we do our actual render loop. So as long as the window is not closing, we're going to check for a bunch of keys, and we're going to use that to control our camera. Then we're going to update all our sprites using multiple threads. So we're basically going to launch, in this case, we're going to launch 4 tasks, and each task is going to loop over its own range of sprites and just do updating stuff. This is all on the CPU. We have to realize it to a vector in order to get the tasks actually launched. But we don't store the vector anyway, so it immediately, once it creates these 4 vectors, it immediately tries to destroy them, which will block and wait for the futures to finish. So a very nice thing here, we launch 4 batches of sprites running concurrently, and then we join up into here, essentially. So here I'm just checking how long it takes to update all the sprites, completely CPU operations. Then we begin the frame to render, so we call the pane begin frame for each batcher. We're going to start a batch and give it its command list and its fence values. And then for each batch, we're going to loop over all the sprites in that batch and draw it to the batcher, which is going to use it's going to find out which sprite frame is associated with the current sprite instance animation, and it's going to use that sprite frame to draw itself to the batcher. And again, we do our trick here where we realize it to a vector, and it's going to block here. And then when that's all done, then we submit the 4 batchers in order to the command list. And then we end the frame, and then everything is done. And we just loop like this. And when we click the close on the window, it's going to exit this while loop. It's going to make sure to flush all the queues so we don't have any, dangling resources. And then when it exits here, it is going to free up all the pane and all the other stuff that we created in here for graphics. Make sure all of our resources are nicely cleaned up. And the last thing it does before it exits is it sets this atomic bool so that the main thread can see that, this window is dead. I can erase it from the container, which calls its destructor and removes it completely. So there you go. There's how the whole shebang works. And if we run it like it is right now, I changed the number of windows from 1 to 2. And so you can see here, I've got 2 windows rendering the same scene. Well, they're not exactly the same, maybe. I think perhaps they might be exactly the same. I think they might use the same random seed now that I think about it. Sorry, I have to compare. No, they seem different. Yeah, they look different to me, so they're not using the same random seed. But here they are. And I can use the keyboard to navigate around here. I can rotate the camera, and I can zoom out and zoom in, zoom. Beautiful. I can close one of them. The other one stays alive. It's still chugging along. They are completely independent of each other. We can see here with 1,000 sprites, to update the sprites takes like 16 microseconds, and to draw all the sprites takes 30 microseconds. Well, to submit the drawing command. So it's very little, and that scales again, like I said, up until like 500,000 sprites, which is, by the way, way more than you're freaking ever gonna need. Like if you look at actual games that people release, like the typical games like Stardew Valley or like Factorio, right? They're not pushing anywhere near that number of sprites. They don't need anything near that. And even like the outliers, like your extreme bullet hells, they're still pushing, like thousands of sprites. Yes, generally not tens of thousands, and certainly not hundreds of thousands. All right, so that's part 1 done. This video is a long one, but I assumed it was going to be, and it doesn't bother me too much because this video is, it's probably going to be removed from the playlist at some time in the future, just archived somewhere. But I figure it is nice to keep you guys in the loop, and like I said, I gotta debrief Fox. I'm just looking at my microphone here. Okay, we're not in a blizzard. It is not misbehaving. Cool. So the second part here is just like, all right, so what are the things that I'm grappling with? What am I having trouble reconciling all my different requirements and all my different wishes and hopes and dreams? And also what I think the next steps going forward look like. So my goals here, you probably know some of them, but I want all these interfaces, all these different components to be extendable, to be customizable. So you can basically, change the framework any way you want, inject the different parts of the framework that you changed without touching the base source code, which makes upgrading a lot easier if you want to upgrade to a new version of the framework. I want it to be, very extendable. So we got to have lots of virtual functions that you can override in interfaces. We want to make it more granular. So instead of having big monolithic objects that you have to fully implement, if you want to change one aspect of the sprite batcher, you can just find the sub-object that is responsible for that aspect and just implement it with your own desired behavior and just inject that sub-object into the IOC, and that will change how the sprite batcher works. That sort of idea. And, there's different ways of achieving that with, the virtual interface and with increasing composition of the different objects, and also just with parameterization of, like the constructors or maybe some setter functions that you can call after construction to customize the objects. But yeah, that's a very big goal. These aren't in any particular order, by the way, just whatever I thought of at the time when I was writing the list. The other thing I need to be able to do is like to use the IOC to resolve interfaces. So for example, I've got some problems there that I have to handle, like the resource loader. It's creating a concrete texture in here, but that's no good. I want it to use the IOC to create the texture so that if you inject a different implementation, it will use that one to create the texture. You can customize texture then. If I hard code it to use this implementation, then it's not very configurable. It's not very customizable, is it? But now, well, how do I do? Do I call the IOC from in here? Then I'm coupling this thing to the IOC, which I wanted to keep it decoupled. I'm like, how do I do that? And maybe I don't. Maybe I just live with the fact, okay, all the things I make here are going to require IOC. You can't use them separate from the IOC, which is a bit of a bummer, but it's a thing that I thought I might have to do. But we'll see. Again, I want to definitely get separation between the platform independent layer and the platform specific layer. I haven't done that. I've only started at a little bit here, but that is going to be expanded. That's actually one of the first tasks that I have on my steps forward here. Another goal is as much as possible to move things out of the platform specific layer and into the independent layer, because platform specific layer needs to be implemented X times per platform that you support, whereas the independent layer, you implement it once and it works for everything. So that's obviously the way you want to go, but some things need to be in the platform specific layer and some things would like to be because it makes it more efficient. So you have to, there's a trade-offs that come up in here. Supporting very large draw rates is obviously a goal that we would like to have, and that has already basically been achieved. Maybe I might run into, like if I want to try to implement other effects, I might run into issues and have to rethink. At the time being, I'm very happy with the performance that I'm getting with this prototype. There's not, we could look at ways to make it better, but if it never gets better than the way it is right now, that's already more than is necessary in my opinion. So here's another big one that is going to be important. Right now it's to get to render sprites, you got to create a bunch of stuff, right? You got to create all sorts of things. You got to create the pane, the device, you got to create the batcher, the codecs, and all that stuff. I would like to have a very simple layer where it's like you have one function that creates a window, and you have one function that creates a sprite, and then you can just draw that sprite to the window. So it's like 3 steps. So very similar to what you can do in something like SFML, and all those details will be hidden away. And so there will be I want a simple, dirt stupid layer for beginners to muck around with the framework, using it to create very simple applications for learning purposes, for practicing C++, and for maybe like a little bit of a gateway drug into the real framework. So we definitely want to have a very simple interface. That'll be great for getting interest from a bunch of different users, for increasing adoption rates and stuff like that. It'd just be fun to have. You can then use this to like make very simple videos, tutorials on making simple games and stuff like that. And you don't need all the customizability and all the different, performance enhancements that you can get with the full framework to do these simple tasks. So it would be very nice to have a simple layer. I would like to, in the future, create an implementation layer other than D12. The goodest candidate is Vulkan because it's very similar to D12. But I would like to try other ones like OpenGL or D11 because they work in a different way that will test the flexibility of the interface that we create on the platform agnostic layer, whether that interface is sufficient to encompass all of these or whether it's too much, D12 pilled, Vulkan pilled. So ideally, we would like to craft that interface so that it could support any platform that you want to support. So trying to implement one of these would be a good test of that and a good way to refine the public interface. But there are some features that I am using that I don't know how it's going to work for D11. For example, the way I have the sprite codecs where you can index into different textures dynamically in the shader, that might not be supported in D11. We'll have to look. Or OpenGL. I'll have to see. The other thing is, one of the goals that I'm doing in here is I want to support the multi-window, multi-swap chain use case. That's one of the neat things I want to push with this framework. And that might give a problem with D11. Because with D11, I tried it out and it did not work. It did not work well. Trying multiple swap chains, multiple threads. So there might have to be like a crazy, kludgy shim in order to get this stuff working with the current system where you support, multiple windows, multiple swap chains. That might be hard. And the answer might be that certain backends just only support one window. But if it's not the case, the other answer might be that you have to actually have a device per pane, in which case the iDevice interface would just be a kind of dummy and a weird mapping layer. But I don't know. I've got some ideas, but it's not going to be an easy one to solve. Yeah, I would like to minimize the platform agnostic API layer. Shouldn't have too much stuff in it that is only really applicable for a specific platform, but sometimes you got to put those things in there just to encompass them all. So, which one of the goals is to minimize that, but it's going to be a give and take, a little bit of a tug of war there. This one is a little inscrutable by reading it. Probably won't make a lot of sense to people, but basically, you're going to have a bunch of, platform independent interfaces, and they're going to be implemented in these classes in here. But you can't mix and match. So you can't mix like a sprite batcher from D12 with a command queue from Vulkan, for example. That's just not going to make any sense. So the question is, how does that live in the IOC injection world where you can inject, individual components freely? We would like to make some kind of a thing that lets you know if you're being stupid and you're using incompatible components together. So maybe there's like a thing, a layer above the individual components that basically groups them all together and says, these are all the ones that goes together and let's inject them all at once into the IOC container. Maybe. I don't know. And also, there might become a case where, there might be variants of command queue, but they only work with like command queue in D12, but they only work with specific variants of render pane in D12 or something. So these things might not all be completely independent. You want to make them as independent as possible and as mix and matchy as possible. But some of them might require other ones that are compatible. Like when I break the sprite batcher up into smaller composed things, for example, the effect things like I might have like a component for the constant buffers, and then I might have another component that you can inject for the shaders, but obviously certain shaders go with certain constant buffers, and there might be some degree of freedom, like there might be a set of constant buffers that are compatible with a particular shader, but not all constant buffers will be compatible with all shaders. So there's going to be some weirdness there to think about in terms of how to group compatible things together and how to validate that compatible things are being used together. Other things like, for example, for the interfaces for the sprite batcher. Like if you look at the draw interface, it's taking in position, it's taking in rotation and scale. But sometimes you don't need rotation and scale. Like for example, if you're drawing a tile map, you don't want rotation and scale. And so it's an optimization to be able to remove that from the vertex information that has to get transferred over the buffer or over the bus. And it's an optimization to now not need to do those calculations in the shader. So maybe we would like to inject, a shader implementation into our batcher that doesn't do those things. But then this interface doesn't make any sense. But this is part of the public interface. So like that's not compatible with the idea of a simpler shader that doesn't do rotation or scaling. So how do we reconcile these, these tensions here? There's lots of tensions involved in here. Another thing is like, doing more work on the CPU versus on the GPU, and how does that change the interfaces between the different objects? So this bears thinking. This is, again, going together with stuff like this and stuff like this. It's just, how instead of having to re-implement a batcher for every different effect, it'd be nice to use the same batcher class and just, inject different effects into that class. And injecting an effect means, injecting the shaders that are being used and the constant buffers that are being used. And maybe some of the functions that are used to set up the data that goes into those things. So subcomponents, right? And then there's a question of how much do you separate the subcomponents? Like, do you make the shader and the constant buffer independent, or do you make it so they have to be a package that you put together in there, and that'll prevent being able to put in incompatible ones, matching them up? I don't know, man. And this is again together kind of with the effects and the shaders for the sprite batch, but there are different ways of how we handle processing of the coordinates and how we interpret them. And we would like to support those different modes, like whether you want things to be snapping pixel perfect or whether they don't have to be exactly pixel perfect, and how you handle, if you want like quote unquote pixel art games where they're very chunky pixels. Usually you don't store the sprites with that chunkiness. So now how do you handle upscaling those chunks to maintain the pixel correctness? And how does that work with rotating? When you rotate things, do they stay square pixels on the screen, or do the chunky squares rotate as well? There are different ways of handling that, and we would like to support those different use cases out of the box because they're all common use cases that being used by different games. All right, so those are some of the goals. This is not an exhaustive list probably, but those are the ones I could think of. Now, what are my steps forward? Well, the first thing I want to do is I want to draft the platform independent layer interfacing. Actually, so I've already done a lot of that work. You can see here, I put now all the things that are going to be so far that I've decided should go into, I don't know what you call it, the agnostic layer. They're in here. They all have their just their pure virtual interfaces defined in here. And they're going to be interacted. I need to now put these into the IOC because right now Window app is still creating specific ones. So it's still, binding when it creates like a command queue, it's binding to D12. But it should not do this. It should use the IOC to resolve all these out. So that's the next step. That's here actually. Test integration with IOC. This one is done. This one's already done. But I want to test the integration with IOC. And then once I get that done, I want to draft just an idea of a simple mode API, what that looks like, just for creating a window and drawing a texture and just making it as the use case as simple as possible and moving from there. Then I want to talk what I was doing before, like I want to break up monolithic classes like sprite, batcher into more composed classes. So composed of sub components. And then I want to add the ability to customize Sprite Batch by being able to inject effects, which will be subcomponents, hopefully, once I've broken that up. And the next thing is implement text rendering, because I want to implement a bare feature of like, what are the things that I want this graphics layer to be capable of? What are the main use cases? And I've outlined them here, but it's basically sprite drawing, and with animated sprites. Those are things that we're going to build on top of this. But also drawing tile maps, particle system, big one, text, and then, basic shapes and custom 2D poly meshes. So these are all the things that you will be able to draw with our 2D framework. These are the graphics primitives that we want to support out of the box. And in order to understand what the final interface and the final system is going to look like, I have to implement at least, like most of these. That's really going to tell me, what I'm missing and, what assumptions I made are just totally wrong. So the next step is, implement text rendering and then also take a look at what the simple mode version of text rendering looks like. And then I want to start creating higher level constructs. Like I did a very just hacked up version of a higher level construct of an animated sprite, but I think I got to dig deeper and say, okay, so what's a real good animated sprite layer going to look like? What's a tile map layer going to look like? Text like that, just the high level things that are going to be built on top of the low level and that are going to live in this graphics folder. And then once we've built all these things, try to see how much we can move from the platform dependent stuff into the independent layer. Then another thing I'd like to try is a couple of implementations, different implementations of the graphics interface. We now got the interface. We got a bunch of stuff that's built on top of it. It's working. Can we now add a different low-level implementation using the current interface? Is it sufficient to support different platforms? And if we swap them in and out, can we just render the same graphics in more or less the same way? And we want to try that with Vulkan, which should be possible because of its similarity with the way it works and D12. And then we want to try a harder one like D11 or OpenGL and see, really push the interface definition to its limits and see if it can support using a much different backend. Another thing that I want to do is I want to set up some comparative benchmarks with the things that will compete with the chill framework. Just to set up a baseline to make sure that we're not doing way worse than them. I don't think we will be. I think we'll be doing much better because these ones don't, I looked into SFML. It does not support sprite batching out of the box. You have to do a lot of manual lifting to get sprite batching working. And so that's not great. That it makes the sprite and the texture classes by themselves kind of useless, except in the very trivial use cases where you're drawing very few sprites. And I don't know about SDL, but I think it's probably a similar story. You got to do a lot of the heavy lifting yourself. And we're going to have batching, even in simple mode, it will be batching your sprites. So you'll get very good performance with a very simple API and very clean. All the resources are taken care of. You don't have to manually free everything. I think it's going to be great, but we want to have these benchmarks in place just to verify. So exactly the same scenarios, exactly the same top level layers, of the game logic and just replace it with these ones as the final implementations of how that game logic is rendered to the screen. And another thing we would like to do is explore a few alternate implementations, like within D12, a different sprite batcher. Can we do a sprite batcher that does like all of the work on the GPU, more of the work on the GPU using like, I don't know, like indirect command list or something? Maybe storing more sprite information on the GPU, and how would that work? Just really trying to push the interface to its limits to see what is possible in terms of how much you can change the behavior. So yeah, those are my ideas for, I think, what's going to be necessary before we can finalize the graphics system and then actually, make the videos on it and go step by step building the pieces up in the video series. And then we can move on to other stuff as well. But yeah, it's a lot. I think it's a lot. Maybe it's not as much as I think. But my main takeaway is, and over the last few months, I haven't had a lot of time to work on this stuff, which is the main problem. But another problem is that I'm kind of avoiding it too, because I'm like, there's so many conflicting goals and aspirations, and I'm having a trouble like getting a kind of like a eureka moment where it's just, if I do things this way, it'll solve all my problems. And it's like I'm waiting around for like something to hit me, but I don't think I think we just gotta like build what we can build and then iteratively try to make it better and move towards what the ideal is. And we'll never reach the ideal, but we got to get close as possible. We just gotta start with something and get something down. And I've been doing that, like that's what this is, but I gotta do it more. And I gotta move further and further and just push it down the line, even though I know it's not the perfect thing that I want to make. As I implement more of it, hopefully the path will open up to a certain extent. And when I bring, Fox on, if Fox is, if Fox is down to clown, I think he'll be able to bring a lot of good ideas to the table. And hopefully we can, we'll get something. Hopefully it will be something that is fairly close to what I aspire it to be. But that's everything. So everything for you guys out there in Planet Chili, and specifically Red Skittle Fox. Here it is, and I would be interested in. We'll meet up on Discord, and maybe take some notes on your thoughts and your questions, and we will hash it out. And we'll see what you can do. Maybe something in this list is something you might be able to tackle. And also, I want to hear all your ideas on the architecture and how it can be changed, the current one, and all that good stuff. So I'll see you guys sometime in the future, and I will see Red Skittle Fox hopefully, pretty soon, within a week or so. All right, that's it. All done. Thanks for watching. Hope you enjoyed the video. Click the like button, all the good stuff, and I will see you again with some more chill.